In this section we will study more about ground grid systems or earth mat systems. So let us see what is the definition of an earth mat or a ground grid. So according to IEEE, a solid metallic plate or a system of closely spaced bare conductors that are connected to and often placed in shallow depths above a ground or elsewhere at the earth's surface in order to obtain an extra protective measure minimizing the danger of the exposure to high step or touch voltages in a critical operating area or places that are frequently used by people. So this is the IEEE definition for what an earth mat or a ground grid is. So basically a ground grid is a system of bare conductors that are buried below the earth's surface or above the earth's surface, which is used for protective purposes. So why we need earth grids or the earth mat? So the purpose is to prevent electric shock and to mitigate over voltages that can damage equipment. So in substations, high voltages line carry alternating currents which can induce voltages on conductors. So this means that the steel structures in and around live equipment will pose a shock hazard. Even when the fence is enclosing the substation will have induced voltages when high voltage transmission line passes overhead. So it is essential to ground on all the above conductive structures to mitigate the shock hazard. And next we will discuss about what is the step potential. So step potential is the step voltage between the feet of a person standing near an energized ground object. So it is equal to the difference in voltage given by the voltage distribution curve between the 2 points at different distances from the electrode. So during a fault, a large voltage will be induced in all the other conductors in the substation. So if we are about to touch these conductors, we will have a shock because the fault current causes induced voltage on these equipments. Then there will be a ground potential rise, and because our 2 feet are at 2 points, then there will be a resistance between them or a potential difference between them. So this causes the step potential. And next is the touch potential. So touch potential is much simpler than the step potential. Touch potential is the touch voltage between the energized object and the feet of a person in contact with the object. So this is equal to the difference in voltage between the object and a point some distance away. So let me show this graphically. So the transmission tower will have induced currents flowing through it. So over my right side we have a person touching the transmission line. So this is the touch potential from here to here. That is the point from he is touching with his hand and to his feet at the ground. The voltage between these 2 points is called the touch potential. Whereas in the case of step potential, the step potential will have the induced current flowing from the tower to the person's feet. Because these 2 feet are at different positions or different points, then the potential difference will cause a current to flow through the legs of the person. So as you can see, the touch potential is much severe than the step potential, because the path of the current is through the heart in the touch potential, whereas in the step potential the current path is only through the legs. So next we will look at the tolerable voltages. So the touch potential for a person having 50 kg weight is given by this equation over here, where CS is the surface layer derating factor. This is the correction factor we use because in substations, in order to minimize the step potential, we usually place granite rocks or crushed rocks, and in order to correct the actual soil resistivity, we use this term over here, the correction factor, considering the effect of the crushed rock. And this is the step potential for a 50 kg person. and this PS or the rho S is called the soil resistivity and is given in ohm meters, and the TS is the maximum fault clearing time in seconds. Then the next term is the split factor. So not all the fault current will flow back to the earth. A portion of the earth fault current may have another return paths. As a result, the current gets divided at the point of fault, and some of the fault current would go through the overhead earth return cables, buried pipes, and earth conductors, and therefore the current division must be applied to account for the proportion of the fault current flowing back to the remote earth. So in many cases we consider split factor to be 100%. We consider that all the fault current is flowing to the earth, but in actual case there will be a split of the current, and some of the current will flow through the earth conductors and other part of the current will flow to the earth. So we are actually over engineering this so that we do not have any problems regarding our safety. And another factor is that the split factor is very difficult to calculate, and there are other regulations put forward by IEEE in order to calculate the split factor. So in our case and in many cases we use 100% of the split factor. And next is the ground potential rise. So the potential between the local earth and the site is considered to be zero at normal condition. However, when a fault occurs, the flow of current to the earth causes a potential gradient in and around the site. So the maximum potential difference between the site and the earth is known as the ground potential rise, or the GPR. So it is important to note that this is a maximum potential difference, that earth potential around the site will vary relative to this point. So during the period of fault, the potential in the site will increase compared to that of the local earth. So that potential is called the ground potential rise. And in order to verify our earth mat design, actually there are less methods concerned to how a earth mat should be designed. However, there are methods put forward by IEEE standards, but actually the thing to consider is whether the designed earth mat will have mesh voltages or the ground potential rise which is less than the step and touch voltage limits. We also take into consideration of the economic factors such as the price of the conductor and so on. And in ETAP you can perform earth mat design either by using the IEEE 80 standards or by the finite element method. In the finite element method, we will design the earth mat according to our specifications, and we can also plot the 3D graphs as well. So in the next lesson we will design the earth mat in ETAP. So see you in the next lesson.